Hello everyone. In this lecture we will discuss the electric displacement. For this we will discuss Gauss law in the presence of dielectric. So as we know, according to Gauss law in vacuum, del dot E is equals to rho over epsilon naught. That is, divergence of electric field is equals to rho over epsilon naught, or we can write epsilon naught del dot E is equals to rho. So here rho is the volume charge density. So here in case of dielectric, this volume charge density is equals to the sum of the rho B plus rho F. That is charge density due to bound charges and charge density due to free charges. But here charge density due to bound charges is equals to divergence of polarization, that is minus del dot P. So we can write rho is equals to minus del dot P plus rho F. Okay. So now when we substitute the value of rho in question first, then we can write epsilon naught del dot E equals to minus del dot P plus rho F, or we can write del dot epsilon naught E plus P, and this is equals to rho F. So here this factor, that is epsilon naught E plus P, this is equals to D. So here D is known as the electric displacement vector. So this D is the electric displacement vector. So we can write del dot D is equals to rho F. So this is the Gauss law. This is Gauss law in the presence of dielectric. Presence of dielectric. Actually, this is a differential form of Gauss law. Differential form of Gauss law mean divergence of electric displacement vector is equals to the volume charge density due to free charges, and this is a differential form. So in integral form we can write d dot dA, and here we have a closed integral, and this is equals to f enclosed. That is surface integral of electric displacement vector is equals to the free charge enclosed in the volume. So where QF enclosed denotes the total free charge enclosed in the volume. Total free charge enclosed in the volume. Okay. In continuation of this, we will discuss deceptive parallel. Deceptive parallel. Actually, deceptive mean we have some misleading parallels. As we discussed, in the presence of dielectric, Gauss law is del dot D is equals to rho f. So as we discussed, this is the differential form of Gauss law in dielectric, that is divergence of electric displacement vector is equals to the volume charge density for free charges. And second, we have that is divergence of electric field is equals to rho over epsilon naught. So this is Gauss law in vacuum, or we can write epsilon this equals to rho. So this is the equation for Gauss law in presence of dielectric, and this is the Gauss law in the vacuum. So here we have a deceptive parallel, that is it seems that these two relations are equal, but actually this rho f is the volume charge density for the free charges, and this is the volume charge density for total charges. And second point here is we cannot say that this electric displacement vector is equals to this factor. Okay, other reasons we have. First point is the integral of this electric displacement vector is not equals to 1 over 4 pi epsilon naught r cap over r square rho f r dv. So first point, in the integral form the electric displacement vector is not equals to this factor. And second here is as we discussed, del cross E is equals to 0. This is a known concept, that is curl of electric field is equals to 0. But in this case, in case of electric displacement, we know D is equals to epsilon naught E plus P. If we take the curl of this, that is del cross D, this is equals to, we can write epsilon naught del cross E plus del cross P. No doubt this factor is equals to 0, but there is no any general reason, there is no reason in general to suppose that this factor is equals to 0, that del cross P is equals to 0. So in general del cross D is not equals to 0. So these are the we have two basic reasons why they are not equal. First, the integral form of electric displacement vector is not equal to this factor, and second point here is curl of electric displacement vector is not always equals to 0. But on the other hand, if we have a Gauss law in vacuum, then del cross E is equals to 0. Next, we will discuss boundary condition for electric displacement. So here the discontinuity in the component perpendicular to an interface this is d above perpendicular minus d below perpendicular, this is equals to sigma f, that is surface charge density due to free charges. So this is only at the interface. And second, for parallel components, this d above parallel minus d below parallel, this is equals to p above parallel minus p below parallel. So d here is the electric displacement vector and p is the polarization. So here in this lecture we discussed Gauss law in the presence of dielectric, then we discussed the deceptive parallel, and then boundary condition. Okay, thank you.